You're talking about Lee? Yeah, he'll come. Oh, you can call it if you want. Now that Lee is here, we can start. I'm just kidding. He went to look for you.
I went to the wrong place.
Me too, actually. I went to Sky Room.
Okay, so welcome again to this season seminar. And we have Asymptotic talking about BMS group and the subgravitons theorem and all this. So it will be a Blackboard seminar. So
yeah.
Please ask questions, I guess, during the...
Right. So this is kind of an old topic because this BMS group particularly was analyzed in great detail in 50 years ago. And particularly in the 1980s, in general relativity community, certain ideas were developed. And these ideas have been rediscovered in the last 2-3 years, particularly by Strominger's group in Harvard. And they have served as a basis of these new proposals that Hawking, Perry, and Strominger are making about how perhaps information is, in the black hole evaporation process, why it is that the S matrix could be unitary. So what I would like to say is basically give a very pedagogical overview of what is happening, what was known before, what is known now, and a little bit from a more general relativity perspective because of these people here in the strong gravity group. The bottom line, for those of you who might not be interested in too many details, is basically that the structure of the BMS group is completely well understood. There's no problem. Some conservation laws were known, but new conservation laws have been proposed. In the classical theory, as we will see in a minute, we can see if this is true. And indeed, there is a class of spacetimes for which nonlinear spacetimes, solution of Einstein's equations, in which these conservation laws hold. But as we'll see, they hold in a rather trivial sense. So this class of spacetimes is a little bit too restrictive from the point of view of most general relativity people. And then there is an idea that these laws are strongly suggested by soft gravitons theorems, which are through the infrared. And I will tell you about the status of that. There are certain assumptions that are made, certain operators supposed to exist, and these have been challenged by a number of papers recently. And so I'll just tell you about that. So that is the general idea of the talk, but it's going to be pedagogical because there are many students and not everybody has heard about the BMS group. So I'll spend some time about the BMS group to begin with. Okay. So the first thing is just the title there, the BMS group itself. I should just say that almost everything that I'm going to say, except the very last part, is really discussed in many papers in the 1980s. If you want to, so many papers up here, but there's also a book, a little book called Asymptotic Condensation that I wrote in, I think it was based on some lectures I gave in 1984 that contain kind of 2/3 of what I'm going to say. And this book is available in the on one of these websites, ResearchGate website. So you can just look at that book up here. Okay. So now, null infinity and BMS group. So let's begin at the beginning. So basically, The idea is due to Bondi that if you want to study radiation, in particular gravitational radiation, then the structure of the theory would simplify, structure of the analysis would simplify if you went to infinity in null directions starting from the sources. So if you think of this as being time and this as being a source going around, then we are going in the null directions instead of a space-like direction that one is very used to. So that was Bondi's idea up here, go to infinity in null directions. So let us just start with just beginning. So this is the first part, the BMS group. So then let's just begin with Minkowski space and see what happens up here. Again, I hope that it's not too boring to most people, at least, but some people may not know about this. So in Minkowski space, we know that the metric, and I'm going to put hat for physical metric for a minute. You'll see why in a second. So it's going to be d hat squared plus dx squared or dr squared. Let me just put t here. dr squared plus r squared d omega squared. And the idea up here is that if you have some observer going like that, along following a Killing trajectory, then we can look at the future light cones, and these are going to be given by u equal to u0. And u is just defined to be equal to t minus r. And the past light cone would be given by v equal to v0. So these are the light cones up here. And so the v is just given t plus r. And the idea is that these light rays are just null geodesics. And what null infinity does is to just give you the final resting place of this light ray, where the limiting points of these light rays. So basically, we add a boundary to the physical space-time so that each of the geodesics hits this boundary at one and only one place. And this boundary in the future is called Scri plus. And similarly, we add a boundary to the past, which we call Scri minus. Okay. And so what we're doing up here as you go into this boundary is that you're going as u equal to, keeping u constant, and then we're letting r go to infinity. So that's what we're doing up here. So to do that, you see, it's just easy to first write down this metric. Let me just do it for the future. Past is exactly similar. So you can just write down this physical metric as minus du squared plus twice du dr plus r squared d omega squared. Very simple thing. And then the idea is that you want to go to r equal to infinity. Of course, r equal to infinity is not a part of space-time. The coordinate is not well defined there. So we make a confounded completion, defining confound factor to be 1 upon r. So the infinity, or Scri plus, would correspond to omega equal to 0, r equal to infinity, u equal to u naught. That's what we're doing up here. So then if I just substitute up here, you will find quickly that ds hat squared will be equal to minus du squared minus twice du omega upon omega squared plus 1 upon omega squared times d omega squared. So of course, the physical metric blows up. If you go to infinity, the distances become just infinite. So we define a conformal completion, or conformally related metric, which is just given by omega squared times d hat squared. And this metric, of course, is perfectly well defined and is even on the boundary, minus twice du d omega plus little d omega squared. Little d omega squared is just the two-sphere metric up here. So that's what we get. It's perfectly fine metric, no problem. The metric is completely well defined on the boundary up here, and it is infinity. And the advantage of this conformal completion, which was introduced by Penrose, is basically that instead of having to take limits in the physical space-time, worrying about whether limits commute with various operations and so on, you can just do local differential geometry at the boundary. And that's the whole point of this construction up here. So the statement is that this metric, which is a conformally rescale metric, is perfectly well defined at the boundary. Now, I've drawn this Scri like a sloping up here. But in fact, if you look at the metric at omega equal to 0, it's just given by du d omega plus d omega squared. There is no factor up here, which means that this, in fact, is a cylinder. So Scri is really a cylinder in this boundary, and Scri minus similarly would be another cylinder. So attaching a boundary to the future, which is a cylinder, to the past to the cylinder, and they don't really talk to each other. They're just two boundaries sitting up there. And this is going to be important. That's the reason why I'm just mentioning this very quickly. Okay. But now we may want to actually look at, and that's what is important for these conservation laws and so on, in the whole picture where Sky plus is related to Sky minus. In Minkowski space, there's an obvious mapping from Sky plus to Sky minus because every geodesic has two endpoints, and therefore we can see that there's an antipodal mapping, right? It goes reflection in the sphere, it goes the other side up here. So we have a natural mapping between Sky plus, Sky minus in Minkowski space-time. If you are given, no, there's a natural mapping by itself. And then the statement is that, well, can we have such a mapping also in more general space-times? And it's tricky. But let's just understand how to do it, because in more general space-time, if you just look at geodesics, they will cross, there will be no natural mapping up here. So the question is really, can we just use asymptotic structure to set up that mapping? And then the idea is that there is a more sophisticated completion which attaches not only Sky, which attaches not only this null infinity, but also the space-like infinity. And then the statement is the following, that Minkowski space, Minkowski space, if you like, think of this as each point being a two-sphere, think of this as being Minkowski space. So what one is doing there in this new completion is making the Minkowski space and embedding it in a cylinder. In fact, the precise embedding is an Einstein cylinder. So therefore, the statement is that the null boundary that we're talking about, Sky plus, is really a future null cone of this point. And this point is called point at special infinity, or I0. And this is a past null cone of that particular point. Okay, so that's the picture that I got. I can just draw it up here just to keep it here once and for all. So we got some cylinder, and then we can just consider and this is the Minkowski space that I'm talking about up here. This is the Minkowski space that I'm talking about. It's embedded. And this point is a future time like infinity, past time like infinity, and this is I0. This is the future null cone of I0 and past null cone of I0. So this identification between Sky minus and Sky plus that I told you about, which is going to be important if you want to talk about S matrix and so on. That identification there, we did it by going in the space-time. But just take it for granted from me that with this sophisticated this conformal completion, you can just look at the structure at I0 and just set up a correspondence between Sky plus and Sky minus by just looking at the structure at I0. And of course, you get the same correspondence up here. But the reason why this all works is that this I0 in Minkowski space is completely smooth. So you can look at geodesics going through here. You can do all those things. But using that smoothness structure of the whole space-time, including I0, you can set up this correspondence. So that is what happens in Minkowski space-time. So now what we can do is we just look at general space-times, and in general space-times, we want to talk about asymptotic flatness. So we're given some space-time M hat, G hat, AB, and we say that is asymptotically flat if there exists a bigger space-time, NGAB, where M is M hat together with a boundary. And for the moment, I'm just going to talk about Sky plus. You can attach Sky plus, Sky minus. You could also attach I0. At the moment, I'm just attaching Sky plus. So you attach. So this is a new manifold with a boundary, whose boundary is this manifold called Sky plus, where the boundary has topology S2 cross R, just like in Minkowski space, and there exists a conformal factor such that the first thing is that this conformal factor equal to 0 on the boundary. So from now onwards, when the hat is there, that just means it is restricted to the boundary. So this just means and its gradient, on the other hand, is not equal to 0 and Sky plus. What this is telling you is basically that the conformal factor, as like in Minkowski space, falls like 1 upon R. That is what this condition is encapsulating for you. And the second condition, of course, we want is that the metric GAB that on the completion is conformally related to the metric in Minkowski space. I'm sorry, in the physical space-time, conformally related to that. on the physical space-time when I had. And the third condition is just that the stress-energy tensor, so we have got the Einstein tensor satisfying 8 pi g Newton and the stress-energy tensor, and we assume that stress-energy tensor goes to 0 at an appropriate rate. More precisely, we assume that omega to the minus 2 times t hat AB has a smooth limit. Very often people, in fact, in this work, people are just looking at vacuum solutions. So in fact, the third condition is completely unnecessary. So we just have these two conditions. And these are the asymptotically flat spacetimes one considers. And they are asymptotically flat at future null infinity. They were drawn up here. And the statement is that there are many examples. So we have got curve spacetime is an example, of course, but so are stationary spacetimes as stars. Solutions, we have general relativity systems, lots of solutions which are stationary, but there are no radiation. And the question about whether there exists radiating solutions which had made kind of global sky completely, that had been open for a long time, and that was, so for radiation, yeah. This is just saying the stress tensor dies down.
Right,
why this rate?
Yeah, why the stress tensor? So why aren't you just talking about the way the geometry?
Yeah, so you could just put R hat AB.
Right, but then what is it about the Ricci tensor that you care about?
Because we're interested in Einstein's equations from the beginning. It's not, we're not interested in this as a geometric exercise. We're interested in this for general relativity. And so the idea is asymptotically flat space-time, the matter sort of doesn't die. So for example, I mean, if you're in cosmology, this condition is not satisfied. It's not asymptotically flat. So we're interested in Einstein theory. We're not interested in just geometry.
Where the other conditions hold, but number 3 doesn't.
Yeah, it's easy to construct such examples. Yeah. And then, of course, this machinery doesn't hold all the Bondi formalism, Penrose formalism doesn't go through for that. And this follow-up is satisfied by Maxwell fields of compact sources to test that this is not a restrictive condition at all. Okay. Now, what about radiative solutions? Radiative solutions. And there are many radiative solutions. It was not known. But then, since 1990s, Christodoulou and Kleinemann, let me just call it K, they first showed that there is an infinite dimensional family of solutions near Minkowski space. So they gave a Cauchy problem. They specified initial data on a Cauchy surface with Cauchy data which is close to Minkowski space, and did a global analysis to show that in fact you got a nice fall off at future null infinity and the past null infinity, and these conditions are satisfied. And these spacetimes feature very strongly in this recent work, particularly by and this group up here. Okay, so this is the Christodoulou Kleinemann. But then subsequently, there have been, I mean, I'm not giving an exhaustive list, but some of the important highlights. There has been a work by Christian and, I'm writing this thing down because this is less well known, Christian and Delay. They produced a kind of a family which is physically more interesting in that Christodoulou Kleinemann's spacetimes, the metric is not smooth at sky. Those of you who know about general relativity, basically the peeling theorem doesn't hold. The thing that don't fall off at an appropriate rate at null infinity. Whereas Christian Delay thing, the spacetimes are Ck for any k, and therefore the peeling holds, everything is much nicer. It's nice. And then there are also a lot of work by Helmut Friedrich, where also the peeling holds completely. In fact, Friedrich has no problem in making the space-time C infinity. So there are all these works which say that there are radiative solutions, but they are all near Minkowski space or near Schwarzschild space-time. One doesn't have control on the space of all asymptotically flat space-times.
Yeah, I don't remember so clearly, but in the original Christodoulou-Kleinemann theorem, it seemed to me that arguably they didn't actually explore a whole open neighborhood of Minkowski space. It's true, it's an infinite dimensional family, but it seemed that they imposed, if I'm remembering right, fall-off conditions that were a little stronger.
No, I think it's a neighborhood.
So
it is a neighborhood. It's an appropriate, yeah, appropriate function space. Yeah, absolutely. So some appropriate function space is a neighborhood. But the statement is that it is indeed the case, in my view, that the boundary conditions are a little bit too strong, and that, they're both too strong and too weak. It depends on how you look at it.
Yeah, from your other example, too weak maybe. But so I'm just wondering if the subsequent work relaxed the boundary conditions.
Yes, they're boundary, but I mean they allow. For example, it's not stability of Minkowski space anymore. So you could have curves. In fact, the crucial delay they talk about the curve family at near infinity. So it approaches curve metric near infinity. They use the gluing techniques that have shown and Corvino and these people in order to construct the initial data of some point, and then they use a mixture of elliptic hyperbolic methods from Friedrich to show that these solutions exist. Okay, so we have these solutions, and now what we want to know is really what is the first of all, what is the difference between Minkowski space? So there are two subtleties that I just want to point out. In the general curve space time, which is not Minkowski space. The first subtlety is that the metric GAB, the physical conform. So if we attach I0 and chi minus, not just chi plus, but attached everything, then the physical metric, then the completed metric, conformal metric. So this notion took a long time to develop, but it was developed, I think by there's some joint work with Richard Hansen that I did in the late 70s. So it really shows that one can do this at completely attachment. There's a nice definition, and the conformal metric, however, is C dot, but not C1 at I0. And this is important because what happens is that in this general curve space-time, so let me divorce it from Minkowski space-time and just look at a neighborhood of this point I0. So the physical space-time is here. This is I0, this is chi plus, and this is chi minus. So in the general space-time, what happens is that as you approach I0 in various directions, then the connection or the derivatives of the metric of the Christophers admit different limits. So the metric is not C1, and in fact, the ADM4 momentum, or ADM mass, is a measure of the discontinuity of the derivative operator or of the Christoffel symbols. So this is important because now the statement is that we had hoped beforehand that maybe we can set up a correspondence between chi plus and chi minus for scattering theory, but we would need that, and that is assumed in the work that Andy and other people do. And so therefore this correspondence is going to be tricky now because the metric is not C1, therefore the methods I was telling you, you cannot go inside and look at geodesics, and you can hope to do it through Scry, and that becomes much, much more tricky. I don't want to go into details about where we are and how much we understand what is true and what is not true, but I just want to point out that this is a subtlety that you have to worry about, and that has not been worried about with adequate care so far. And the second important thing is surprising, and this was a big surprise when Bondi and all these people did it in a long, long time ago in 1960s. The big surprise was the following, that you think that these metrics which satisfy this condition become Minkowskian at infinity. So you expect and that the physical metric G hat AB behaves like eta hat AB, the Minkowski metric plus terms of the order of 1 upon R, the Cartesian components of, you can use a Cartesian chart given by eta hat AB, and the Cartesian components all fall off like 1 upon R in appropriate sense. One would like to say that that is the case. And yes, you can, but this metric eta hat AB is not unique. So even at infinity, if you have gravitational waves, then these gravitational waves leave some ripples even near infinity, so that you cannot extract out a unique Minkowski metric there. So why does this happen? Well, a simple way to understand this is that supposing I got this Minkowski metric, and supposing therefore I got this Cartesian coordinate x hat, y hat, z hat, and t hat, and And then the metric is just given by dx hat squared plus dy hat squared plus dz hat squared plus minus dt hat squared. That is what is given to me. And now I come and make a translation. So I define x bar to be equal to, or let me leave this as it is, and let me just do t bar to be equal to t hat plus a constant. If I do it a constant, there's no problem. The metric is the same. But now I make an angle-dependent translation. So it does not depend on r and t, but depends on angle up here. So if I did that, then of course I can consider the metric eta bar AB defined by the new coordinates. X bar is x hat, y bar is y hat, z bar is z hat, t is just given by that. I can consider such a metric up here. And you can easily check that the difference between this metric is also of the order of 1 upon r. And therefore, the statement is that if g hat AB approaches eta hat up to 1 upon r, it also approaches eta bar up to 1 upon r. But eta bar is different from eta hat even at infinity because of this angle dependence up here. I could write down the charts for you and show it, but let me just go on and just take my word that these are distinct metrics even at infinity. What is distinct about them? Well, you can easily check that if I looked at the time translation killing vector or space translation or anything like that, then the time translation killing vector becomes the time translation killing vector field of the other metric plus terms of the order of 1 upon r. So at infinity, the two time translations, space translations, etc. are the same. So translations of the two metrics will agree at infinity. But the Lorentz transformations, they don't. You know that in Lorentz transformations, they actually diverge as r. So therefore, this factor comes up, and you get a mixing of translation with mixing of this angle-dependent translation with the Lorentz transformations. But Lorentz transformations are not the same. So this means that if you wanted to look at the asymptotic symmetry group, I'm making it plausible first and then tell you the hard result. So if you want to look at the asymptotic symmetry group, you will have to add together Poincare group of eta hat AB, eta bar AB, etc., etc. Put them all together, right? Because this metric is approaching all these metrics together up here. And these Poincare groups in the given physical space-time, they're distinct from each other. And as a result, the asymptotic symmetry group, the BMS group, asymptotic symmetry group, is not the Poincare group, but this group is a semi-direct product of the Lorentz group, exactly as you expect, but with a spacer, with a super translations. Super translation group, which are just angle-dependent translations, and therefore it is independent. So super translation in physical space-time are angle-dependent translations, and therefore the group is actually infinite dimensional. Remember the Poincare group. So this is a cute symbol for Poincare in French, right? This is point, this is carré. So this is the Poincare group is equal to the translation group with semi-direct product of the Lorentz group, but here we get this enlargement, this infinite enlargement. And this enlargement is at the heart of many of the discussions that are happening, that are being talked about today. Okay, so these are the two subtleties, and this is something that people have known for a very long time, second one. The first one is also something we have known for a long time, but roughly speaking, since the late 70s, early 80s. Okay, so now finally, I just want to tell you more formal way of talking about the BMS group, and then we can. More formal way of understanding the BMS group. So what happens is the following, that given any asymptotically flat space-time, I can do a completion, M hat MGAB. This is the completion, conformal completion. And once I do this conformal completion, we can look at the Scri, just look at Scri plus. So now I'm going back to just Scri plus. Look at Scri plus. Scri plus is 2 cross R, signal boundary that is given to you. And therefore, we can take the conformal rescale metric, and we can pull it back to Scri plus. and this metric I'm going to call QAB. So if you pull back the metric, Scry is a null surface, and therefore this pullback of the metric is going to be degenerate, and it has signature 0 plus plus. It is this direction up here is the degenerate direction, and these two directions are space-like, and that is a two-sphere metric. So that becomes, so this is the metric which becomes degenerate. And then finally, I can also take the null normal to Scry, and this is given by GAB, grad B of omega. Omega is equal to 0, therefore its gradient is normal. I raise its index, I get a null normal to Scry. I evaluate a Scry. And then I get this pair, QAB and NA. And then the statement is that then the statement is that if I look at this pair, QAB and NA, of tensor fields of Scry, this is a universal thing. That is to say, the only freedom I have is this given by omega squared times QAB. So if I change my confounded factor to omega times omega, then I'll get that. And here I get omega to the minus 1 times NA. So I get this equivalence class of pairs, QAB and A, of the degenerate matrix and null normals to Scry. And the interesting thing is that you take any space-time, right? I mean, Vasut comes and does curved space-time. I go and look at some radiative space-time. I do this conformal completion. We'll always obtain the same pairs, QAB and A. And of course, these are such that QAB is 0 plus plus, NA is normal to Scry. And there are some conditions between them. Q times N is 0, derivative of Q by N is 0, etc. There are some conditions that are there that are given to you. So the statement is that this is called the universal structure. The idea that Scry has a topology S2 cross R and is equipped with this pair, this is the universal structure.
So omega a function of all the...
Yeah, omega is a function of u theta phi, but it's never equal to 0. Because we wanted grad omega not to be equal to 0. So this omega should not be 0. So it should not go to 0 faster. So the statement is that this actually is the normal, and you get this. This is the universal structure. And now we can just take Scry with the topology S2 cross R with this universal structure and ask for all diffeomorphisms which preserve this universal structure. The BMS group B is the space of diffeomorphisms that preserve this structure. So you don't have to worry about these heuristics where we talked about Minkowski metric and such things, right? We talked about many Minkowski metrics and such things. It's just that you can just do it very neatly in terms of conformal completion, and that is a BMS group. Okay, so that is a long story and took quite some time, but that is the first part. Now I want to talk about the second part, which has to do with the conservation laws. So now what we would like to do is to talk about what are radiative modes of the gravitational fields of full GR, full nonlinear GR. And the interesting thing is that, of course, in the space-time, you cannot separate out radiative modes at all. But if you go far away from sources, and that's what Bondi wanted to do in null directions, then we can. And so what are these radiative modes? And there's a very pretty geometry here that you like, I think, which is the following. That, you see, we look at all this asymptotically flat space-time, and look at any one of them, and you'll always get QAB and A. So that has no information about the space-time at all. You could have a space-time which is stationary, which could be radiating, etc. You'll get exactly the same thing. So where would the information about radiation lie? Now, all of you who are taking courses in general relativity or differential geometry would know that, well, if you want to go deeper, you should look for a connection, right? The derivative operator. That is deeper than looking at the normals and the metric, because it has to do with derivatives of the metric, if you like. And indeed, if you look at this derivative operator grad, you can pull it back to Scry, and that defines on Scry It's not even a statement, I'm just stating you, a well-defined derivative operator. Okay? So we get, and what equations does derivative satisfy? Well, not very surprisingly, you won't be surprised that in fact I got this universal metric QAB, which came from the same. So I'm looking at the conformal completion, which is, I'm given some conformal completion GAB, then I can just do that. So it satisfies that condition, and it also satisfies that it kills the null normal. This is something that you can check just using Einstein's equations, or that follow-up of the stress area tensor, that this actually is true, that DAMB is actually 0. Good. So that's what you would expect in some sense, because there's a universal structure, and now space-time comes and gives you some information about what is going to be radiation. But that information should be compatible with the universal structure, and it is. Now, again, those of you who have taken elementary courses in differential geometry would say, wait a minute, but this kills the metric. Therefore, isn't this unique? So how can it have radiated information? The answer is no. The reason is because QAB is not a degenerate metric. It's actually, sorry, it's not a non-degenerate metric. It is actually degenerate, right? Because it is degenerate, there are infinitely many derivative operators which are compatible with it. So these conditions allow an infinite dimensional freedom. Now you might say, wait a minute, but you told us that you are making conformal completion. If you give me one conformal completion, you'll get this derivative operator. But now Ted comes and changes the conformal factor, makes it omega prime, multiplying by little omega. Then, of course, the metric Q changes, N changes, and the derivative operator changes also. You can just work it out. And therefore, the conformally invariant information is not contained in the derivative operator, but is contained in the equivalence class of derivative operator, where two are equivalent. I can write down the relation for you explicitly, but conceptually, it is just that the two are equivalent if, in fact, they just come from different conformal rescalings of the physical metric. And now we can ask, how many are there? Such D are there. How many such derivative operators there are? And the answer is exactly, there are as many as there are transverse spaceless modes. So the answer is that given any two derivative operator, any two equivalence classes, D prime minus D. Again, for those in relativity, you can think of this as being a shear tensor. This really as many as there are transverse spaceless. These modes appear. So that means that sigma AB is symmetric. It is transverse, and is spaceless. Q is degenerate, but because QAB and B equal to 0, it doesn't matter which inverse you choose, this condition is meaningful. So there are exactly two modes. So given any two derivative operators which you allow, if you like, and you can take a fiducial one, say that this is my origin, then any other one is completely, the space of connections is an affine space. If you choose a fiducial one, then it becomes a vector space, and any other derivative operator is just labeled by these two functions on a sphere, if you like, or a transverse spaceless tensor, which is tangential to these two spheres. And these are the modes of the gravitational field. Now, the non-trivial fact is that this is done in full general relativity. We did not linearize Einstein's equation. We did not take Fourier transforms. So that is kind of interesting and important. And now those of you who know about gauge theories would say, oh yeah, that's what I would expect. Why? Because if I was doing Yang-Mills theory, and it is also conformally invariant, so I can just go to Scry. The classically, the initial value problem is completely well posed. And there, radiative modes are also contained in the gauge covariant derivative operator on Scry, okay, or if you like, connection on Scry. Pull back of the gauge covariant derivative operator, or pull back of the connection to Scry. And so here is the same thing. So it's always a connection which actually formulates, which also captures the true degrees of freedom, the radiative modes of the gravitational field.
Could you say,
Please.
The inverse of Q doesn't exist
right.
because of the other?
Yeah, so the statement is that Q, it doesn't exist in the sense that it's ambiguous. So I can take Q prime AB to be equal to QAB plus VA and B, where V is arbitrary. It's ambiguous. But because of this condition, the statement is that, yeah, QAB is sigma AB, and hits this, and therefore it doesn't matter whether you choose QAB or Q prime AB or there. Okay, so we got the radiative modes, and now the statement is, again, in the early 80s, Michael Froebel and I constructed the phase space of radiative modes, and this is used in the recent work very heavily, phase space of radiative modes. So gamma radiative just consists of all these equivalence class of derivative operators on Scri. And there is a symplectic structure. I could write it down explicitly, but I don't think it helps. There is a symplectic structure of this space. And we showed, this was work that I had done with Anne Magnon, we showed that if you can start with a covariant phase space of general relativity and just assuming asymptotic flatness, evaluate the symplectic structure on Scri, and we get the same symplectic structure as exists on the radiative phase space. So there's complete compatibility with looking at it from space like Cauchy surface, covariant phase space, space of solutions, or looking at the Scri. There's complete consistency between all these structures. So we get a nice thing. And now, not very surprisingly, BMS group preserves the symplectic structure. So it's a symmetry, not only of the universal structure, if you like, but it's also symmetry in the phase space language, in the space of radiative modes. So let me explain what I mean. I mean, consider Minkowski space for a minute, and consider, say, Klein-Gordon or Maxwell field in Minkowski space. Then if I look at the Poincaré transformations, to begin with, we are interested in them because the symmetry is a background metric. But they also act on the dynamical fields, Klein-Gordon field and Maxwell field, etc. And then there are symmetries because they actually preserve the points of brackets or symplectic structure, and therefore they generate Hamiltonians. The same thing is true up here. The BMS group preserves the symplectic structure. Let's call it like that. The symplectic structure, it preserves the symplectic structure, capital omega, and hence you can compute Hamiltonians. Hence we can compute these Hamiltonians. And what is interesting for the purpose of what people do is to look at just super translations. Not the Lorentz transformation, but the super translations. What are these super translations? They are the BMS vector field C of the type some function of theta and phi times NA, where n is a null normal. So they are all pointing up and down the generators of Scri. So super translations are just taking you up and down generators of Scri, but the amount by which you go up and down depends on that function of theta and phi, and therefore it's not just a rigid translation, but it's an angle-dependent translation, as we saw earlier on when we discussed Minkowski space. So we got this very nice structure up here. These are the super translations. But there's an important point which I think seems to be forgotten in the recent literature, or at least it's not obvious that it's taken care of, namely that if I make a conformal transformation, if I make omega goes to omega prime, which is little omega times omega, then this n goes to n prime, and n prime is going to be, so then n is going to go to omega to the minus 1 times NA, and therefore alpha, to get the same vector field, alpha has to rescale. In other words, alpha is not a function, but alpha is a conformally weighted function. And this is, at least, seems to be overlooked. So it's not just a function on two sphere. You have to specify the confound factor to be able to do that, to be able to give this function to two sphere. All right. Yeah.
So this phase space is not a cotangent bundle, I guess?
No, this phase space is just an affine space, right?
Right.
Exactly.
So how do I think about how the symplectic structure works. Like
Oh,
what is conjugate to what?
Right, so it's not completely conjugate. So it's a second rank, it's a non-degenerate skew symmetric tensor on this infinite dimensional affine space. So affine space is like, it's like this floor, there's no origin, it's just floor up here. And then at each point, I got a tensor. So therefore I got a tensor field. That tensor field is closed, it is skew, and it is non-degenerate at every point.
Right, no, I know what a symplectic structure is, but I mean in this particular phase space.
Right, sure.
Let's see, what am I really asking?
So given any two tangent vectors, it gives you a number, and I can write down for you the formula, but I don't know if it is eliminating.
Maybe you're asking about so-called polarization.
Yeah, that's what I'm thinking, but I mean, you can choose many, I guess.
Yeah. So there is one which is given by the positive and negative frequency decompositions with respect to the translation group. That's what we use to construct the Fock space, but that's a separate. Let me go on. You ask me again if you still have questions. Okay, so this is, and now the question is, what is the Hamiltonian therefore? What is the Hamiltonian if in fact your vector field C is a super translation?
Excuse me, but
Yeah.
are you going to say in which sense this has been overlooked and could be?
Because they keep talking about super translation of function onto sphere, and when it comes to identifying things on sky plus, sky minus, if it's a function, then life is much simpler. But if it's conformally weighted function, then I have to tell you, I have to choose a conformal completion of sky minus, and so to say the same conformal completion on sky plus. Otherwise, you can. So in other words, Leak does one and says, oh, then this function goes to that function, and you come one in which just do conformal rescaling in sky minus, and then you'll find it's a different identification. And this is just not discussed anymore. And I want to give benefit of doubt, but I feel that it is ignored.
But since they meet at I naught as that, and since alpha is only a function of theta and phi, is it possible to just say use the same conformal factor?
Right. So the statement is that we don't know. It's not clear what you mean by the same conformal factor in both. This is a very interesting point. I understand it 90%, but not 100%. So let me postpone it to the end, and then we come back to it. And I think this is a thing that people need to think about more carefully.
So can I ask more questions?
Yeah.
Why do you want to identify sky plus and minus?
Yeah, sure. So the reason they want to do it is because they want to talk about S metrics, and they want to talk about conservation laws and such things. So therefore, what I would like to say is that each, as we see in a minute, the conservation laws have to do with some quantity on sky minus with some quantity on sky plus. So you got given some quantity. So for example, you may want energy momentum, or in a minute super momentum on sky minus. Now I want to know what I mean by the same. So it is, a super momentum, as we'll see in a minute, is generated by Hamiltonian. Now therefore I need to know what I mean by the same super translation on sky minus and sky plus. Then I can compare. I mean, for example, you want to have conservation law in Minkowski space, in which you want to say that the energy of sky minus or past infinity is the same as the energy at future infinity. But to talk about this thing, you should use the same time translation killing vector field, right? I mean, you cannot use one time translation killing vector at minus infinity and another one, because then, of course, it's not true that the energy is conserved, right? So you need this identification. I need to know what I mean by the same super translation at sky minus as on sky plus. Okay, so that's where the whole point.
Is the ambiguity resolved in Minkowski space?
Yeah. So in Minkowski space, it is completely resolved. Let me write it myself, doesn't matter. And then a lot of these theorems in the third part, which I'm almost done with the second part, but a lot of theorems in the third part have to do with perturbative quantum gravity around Minkowski space. And as far as I can see, they are using the I naught of Minkowski space in all this to do this, all this. And that is just not right. So you have to use the physical I naught, right? I mean, the I naught, if you send in some particles, etc., then there is an ADM for momentum, which is non-zero, then that makes I naught not differentiable, and you have to use that structure. If you do order by order, you would never see it, right? If you just keep the same Minkowski space, you would never see it. But that's not the right way to do it. So that is the main point that I want to make. Let me just, I can stop anytime. I mean, so, please ask me questions, and when you are bored, I can stop, right? It's not, if I'm not done with everything, that's okay. So I can write down what this Hamiltonian is. So let me just write down this Hamiltonian. So this Hamiltonian is going to be a function of this derivative operator. And I can write down the formula explicitly without introducing any extra structure. That's what we did in the paper with
the generator of this
super translation. Exactly. So this is a function on the phase space. It generates a canonical transformation, the Hamiltonian vector field, and that just corresponds to taking a Lie derivative of this object with respect to the super translation. And so it's not very surprising. Let me just get the numerical factors right. It's not very surprising as to what it is. It is just so it is just equal to given by 1 upon 16 pi g scri integral scri lead c dA minus dA lead c times LB. Let me say what is LB times. Oh, I didn't tell you one important thing, right? Sorry. The one last important thing that I want to tell you, and I forgot up here. Let me do that and then go back to that. Okay. So we got this connection derivative operator that is given to us, right? And that has a derivative. That has information about the radiative degrees of freedom. So of course, given a derivative operator, any of you would like to compute the curvature, right? That's what the derivative operator is dying to do, to give you the curvature. So we can compute curvature of this D. And now, however, we want gauge invariant part of it. We want conformally invariant part of it, because these derivative operators, when they're conformally rescaled, they have this same physical information. So the conformally invariant part of the curvature is coded, perhaps not very surprisingly, in a symmetric trace-free transverse tensor. And this symmetric transverse tensor is called NAB, and this is, Bondi didn't know about this curvature, etc. This was in the 1980s that we realized that what you call news is actually curvature, that this is the Bondi news tensor. So Bondi news tensor is just the gauge conformally invariant part of the curvature of this connection D. Now very often, and this is what is all done in the entire recent work, people use what is called spatial conformal frames. And they are not unique, but they narrow down the freedom very much. And this spatial conformal factor has the property that the metric QAB you get is a unit two-sphere metric. So if I do that, I mean, then I cannot make this general conformal transformations. The class that I'm allowed is very small. It is only 4-dimensional family, and that corresponds to translations. But let's not worry about it at the moment. We just have this unit two-sphere metric. If it is a unit two-sphere metric, then if I do this, then in this conformal frame, or in any of these frames, where it's unit two-sphere, or these are called Bondi frames. So this is a Bondi conformal frame. And the statement is that in such a Bondi conformal frame, the news tensor is just equal to Lie n of sigma AB or sigma dot AB. So dot of the shear is a news tensor up here, or dot of the derivative operator that we. So you choose a fiducial derivative operator, and then we can just do this with respect to that news tensor. Okay. So here I'm just writing down this news tensor. And now you can write it out explicitly. Yeah.
But the shear is still defined as the Lie derivative of Q with respect to n?
No, shear is not. No, shear is not. Shear is the difference between the two derivatives of the given two derivative operator.
It's not like
what are the two derivative operators?
Thank you. Yeah, thank you. So given any two derivative operators, the difference between them is given by is given by second rank symmetric blah 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 tensor. Okay. Now, thank you. Okay. So now the statement is that fix a D naught such that news tensor of this D i.e. curvature is 0. So consider a trivial connection. Such connections were called vacuum connections. Or classical vacuum. Because the terminology was suggested by Yang-Mills fields. In Yang-Mills theory, if you give me a connection whose field state is 0, we call it classical vacuum. So here we're just looking at any connection whose field state is 0, and we're calling it classical vacuum. And now the statement is that given any operator dA, take one of these classical vacua, doesn't matter which one, whose new density is 0, subtract it out, and then this difference is given by sigma. This will depend on the choice of sigma of this thing that the derivative operator I've chosen up here.
Do we know we can always choose that?
Yeah, we can always choose that. So there exist infinitely many such things. We understand them completely.
Even without fitting around the sphere?
Yes, fitting around the sphere. So it's trivial doesn't mean its curvature is 0. It's only the gauge invariant part, but the curvature is 0. Right? It has the two-sphere part completely. It's completely well defined. Right? So the statement is that there is a formula for the new for the Hamiltonian like that. And now the statement is,
sorry,
please.
So to read that equation, I should think of the derivative operator acting on the tensors to the right of it?
Yeah. So this operates on dA and B.
Okay, and LA is what?
Yeah. LA is any covector such that this is equal to -1. There's a lot of work that goes in showing that all these formula are invariant with respect to the choice of L.
Any null vectors?
It's not null, right? Because the degenerate metrics. This is all intrinsic to Scri.
Any vectors?
So this all
L dot.
operates on N.
This operates, sorry?
This is not the same as NAD first.
No, it's the same as LB. So that's why this bracket.
So they don't act on N, the derivative operators.
I mean, that's why this bracket. I mean, they operate on everything. Okay.
So what they're acting on.
Okay.
Okay.
So, lead C of dA LB minus dA operates on lead C of LB.
And then the volume element?
Yeah, volume element on Scri. So Scri has a natural 3 form epsilon ABC in the given conformal completion, and we just do that. I mean, in the Bondi coordinates, it's just equal to du.
I mean, just induced by the metric of
Yeah.
G.
Yeah. So if in the Bondi frame, it will because you're going to need to sphere metric, it will just be equal to sin theta d theta d phi and then du. So there's a formula for that, and that is done in great detail. And then the statement is that you can write this formula if you wanted. This is identical to. I wrote it like that so that you understand that, as you are saying, that lead C just is what this is saying is lead C of D, right? Because you're removing lead C of L up here. So this is therefore I liked it the previous way better. It is lead C of dA minus dA of lead C operating on LB. So it's really the lead derivative of the connection. That's what is happening here. The lead derivative of the thing that is a dynamical variable.
So that is just proportional to L. It's not.
This.
And the operators operating on L would be something that is just a function of L, not a derivatives of L.
Exactly. Yeah, it will not be.
Neutral derivative.
Exactly. Okay, so then this is just equal to 32 pi g, and then this C was equal to alpha times n. Sorry, 32 pi d times NAD times plus dA dP alpha plus alpha QAB times and now the important point is that this quantity is identically 0 if and only if alpha is a translation. I'm working with the spatial conformal frame. You can do it much more generally, but this just makes it much more simple. And this just means that alpha in the spatial conformal frame is a linear combination of first 4 y lengths. Y0, 0, Y1, and Y11, Y1, 0, Y1 minus 1. So when alpha is just the first 4 spherical harmonics in this thing, then we get a translation. If it is higher spherical harmonics, then you get, so to say, this pure super translations, right, which are not translations. But this division depends on the choice of this Bondi frame. If we change the Bondi frame, translations are well defined completely, but super translations get a little bit of translation. So there is no such thing as pure super translation. There is such thing as pure translation. Okay. So we get some formula like that, and it is this Hamiltonian that people want to take to quantum theory. That's why I wrote it down explicitly. So they want to make this into a Hamiltonian operator by making these connections, if you like, as being, or a News tensor, more precisely, News tensor as an operator, and this is just a C number because this is the label of the super translation, and this is just a C number, this is metric. And so then all the operator that will happen ultimately will be on this News tensor. So News tensor will be operator. Sorry, this is an operator, but the point is that it should be an operator, but it turns out that this is just, it doesn't matter which D you choose in this particular combination. I can explain to you later. Just take it for granted for a minute. Don't want to make that. The reason is because this is a function of only theta and phi, and all the derivative operators are the same in that case. And that follows from the fact that these two conditions are true.
Question.
Yeah.
So there is a symplectic structure such that the algebra of these Hamiltonians is abelian.
These are super translations abelian. But of course, the full BMS group, the algebra is non-abelian. It is a semi-direct product of the, it's a semi-direct sum for the algebra of the abelian infinite-dimensional super translation group with the abelian of the Lorentz transformations. Okay, so this is, so let me just summarize where I am, just 1 second, and then you can ask me, because I think it's long and people are getting lost probably. So the statement is that we got very good understanding of null infinity, and there is a universal structure which has to do with the metric and the null normal, and the BMS group is the one which preserves this universal structure. Once you give me one asymptotically flat metric and look at all the QN pairs, you have seen all asymptotically flat metrics and their QN pairs. It's universal. What changes from one spacetime to another is a next order structure, which is a derivative operator. And beautifully, these derivative operators, the conformally invariant part in them, encode exactly the information about the radiative modes, and their curvature is the Bondi news. And we see here explicitly that if you're going to say a time translation in a Bondi frame, which will be in that case alpha is 1, this QAB NAB is 0 because n is trace free. Therefore, this just goes away, and you just get NAB NAB. So the flux of energy in this Bondi frame is just square of the News tensor NAB NAB. This is exactly the kind of thing you expect in Maxwell theory. The flux of energy is E squared plus B squared, right? That's the kind of thing that we're seeing up here. But this is not linearized gravity. This is full gravity. Sorry, you had a question. That's it. Okay. So now the last part, which has to do with
It's sort of linearized because the stuff is very weak out there.
yeah, it is true. But I did not linearize it and use Minkowski background anywhere. And in fact, we saw that there is subtlety, that there is no canonical Minkowski background. By the way, there was a long discussion in the Warsaw Conference in 1962 when these ideas were first introduced by Bondi and so on. And as you all know, Feynman wrote, or maybe many of you know, Feynman wrote this very nasty letter. And Feynman didn't understand this super translation ambiguity. You just read the whole thing, and that's the point. I mean, he was coming from perturbative gravity. You start with Minkowski space, you get a Minkowski space. What ambiguity is there? Right? You add first order, you add second order, add this Minkowski space. And he just didn't understand that. So even great geniuses have, okay. Now the final part is conservation and then quantum theory. So conservation is very small. So now what Andy does is he is focused on only the Christodoulou-Kleinemann space. So he looks at that, it's fine. So he looks at, Andy just looks at, let's consider now only the nonlinear neighborhood of Minkowski space. Discussed by Okay, so just consider that. And now in that case, the statement is that we have sky plus, we have sky minus. There are no sources. Waves, nonlinear waves come in here and go out. But because we are just a nonlinear neighborhood of Minkowski space, flat closures don't form, and you get, S matrix is okay here. It's class again.
What do you mean by the nonlinear neighborhood?
I mean, I just mean that we are looking at, we're not solving a linearized Einstein's equation. We're solving full nonlinear equation. So we look at the Cauchy data for the full nonlinear theory, look at the Cauchy data for Minkowski space, and we look at a neighborhood of that. It's not tangent vectors, but a neighborhood. So these are all solutions to Einstein's equations with all the nonlinearities completely built in.
Expected in some sense to be not too far from Minkowski.
Right.
Whatever too far means.
Yeah.
Well, no, it's a precise definition. You may not like it. But yeah. The precise definition is that, this is the same thing. I mean, you've got some ball in some subpolar space of radius epsilon. That's what one is considering. And you have to go and you have a heuristic understanding of it. You might have to understand, you might want to understand much better, but that's how they prove theorems, right? Global existence uniqueness theorem are always function analysis theorem. So all these things are tied to choices of subpolar spaces. Okay, so I got this is coming in. And now the question that we want to ask is the following. We want to ask, well, I start with sky minus, I start with sky plus up here. So I can just look at sky minus and calculate the energy momentum. Let me call it P sub t, is because P is just general momentum associated with translations up here. And I can ask, so this is P plus minus, and P plus translation. I can calculate also the form momentum out of here. And we can ask, are the two equal to each other, or they're not equal to each other, right? I mean, is energy momentum conserved in general relativity, where sky plus comes on. But of course, to understand this question, we have to understand what I mean by the same translation here and same translation here. This is the question that you asked me just a while ago. So I think it was in 1978, and Manu and I showed that the answer is energy momentum is conserved. So I'll tell you why it is the case. How we showed that. So what we did was we assumed that there is sky plus, sky minus, and I naught. So this is space-time which are asymptotically flat in all these regimes in a very precise sense. And then for translations, you see, you can identify translations here with tangent space at I naught. And you can identify those translations here with the tangent space at I naught. And therefore, you can relate the past limit of the Bondi form momentum with the ADM form momentum, and the future limit of Bondi form momentum with the ADM form momentum, and we show that they are the same. They are the same so long as the total news coming in here is the flux of the total energy that is radiated, energy momentum that is radiated away is finite. So long as the news tensor falls off at a certain rate, I think it was 1 upon u, 1 plus epsilon, then the statement was that we could show that everything, the energy moment is actually fine, conserved. Now remember, I spent some time early on in trying to explain to you that we have this ambiguity in asymptotically flat space-time as to what we mean by asymptotic Minkowski space. But I told you that all these asymptotic Minkowski spaces have the same translation group. And that is why this ambiguity, you can just choose any one of them and define the translation, and it doesn't matter which one you choose. But for super translations, this is not the case. And that is why there is ambiguity in super translations. This is a delicate point. I'm just telling you this fact. And afterwards, I'll stay and answer questions about this thing up here. So we showed that for energy momentum, it is fine. And the question is now, what about super momentum? Is super momentum conserved? And as I just told you, now we have to worry about the fact that, do I know what I mean by the same super translation on sky minus and the same super translation on sky plus? If I know that, I calculate this quantity on sky plus, I calculate that quantity on sky minus, and ask if they are equal to each other or not. So what does Andy do? He looks at the spaces and he says that these spaces are the properties. This space is the property, one, that if you go to future infinity, I have to tell you one more thing before I, can I get by? So one, that the news tensor dies. So if you go to future infinity, the news tensor dies. If you go to I0, it dies. I0, it dies, and this thing is here, it dies. So that all these formulae that we've written down are perfectly well defined.
This is a requirement or
This is true for this class of space-times that they actually show. So they give you initial data, they evolve it, and then the statement is that this class of initial data has the property that news tensor dies. In fact, it dies as 1 upon u squared or square minus, square plus, and 1 upon v squared and square minus for this class of space-times. At least as fast as that. Okay, so that's it. But then there is a second requirement, and for that I need a little bit your indulgence. Is one more thing that I forgot to do up here, which is the following. This, we said, is the flux of energy carried by nonlinear gravitational waves, or supermomentum in general. If alpha is one of the first 4 YLMs, then it will be energy momentum. In general, it is supermomentum. So we can ask that if I got this sky, and if I give myself 2 cross sections, right? If you give me 2 cross sections up here, then this flux through this little region up here is the energy momentum or supermomentum that is carried away. But can I define a charge integral up here so that the difference between them is actually this supermomentum that is carried away? So there's a balance law, and indeed there's a balance law. And this, of course, is the balance law Bondi's, but we showed it in this phase space framework very directly, that this balance law is that I can define, there's this P-C, if you like. I can define a quantity P-C associated with the cross-section C of sky, and this is defined to be equal to 1 upon something. So some normalizing factor, maybe it's irrelevant. 1 upon 8 pi g. Cross section up here times alpha times a certain real part of psi 2 naught. And those of you know this is some component of the Y tensor at evaluated sky. This not just means evaluated sky plus leading order term, if you like, plus 1/2 times alpha times NAB times sigma AB. So the idea is that you give me a cross section and a super translation, and I give you a charge integral. You give me another cross section, and I give you this charge integral. And then the statement is that P of C1, C2 minus P of C1 is equal to the integral of this flux that I wrote down up here. So let me just call this whole thing flux associated with V3 sky. So this evaluated in between that in this little region bounded by these two surfaces, it gives you this. So there's a balance law up here.
So this is sort of a conserved current.
It's like a conserved current, right? Exactly. But I like to better call it balance law. The reason is because these people want to use the conservation term, conserve or conservation, to go from sky minus to sky plus. So here, let me just call it balance law. Morally, it is exactly what you say.
What is the knot on psi indicating?
Okay. So what happens is the Y tensor actually vanishes at sky. So you take omega to the -1 times the Y tensor, and that's why this knot is that. It just refers to the leading order part, which is in the. Okay. So the second thing that this crystal Klein show is that, so if the news tensor vanishes, then this term is 0. But they also shows that if I go to I plus and I naught, you see all the mass has disappeared up here. Therefore, you would expect that in the distant future, the charge integral would actually be 0. So, and they show that is the case, namely that psi 2 naught also goes to 0 at I plus and I minus. So as you go up here, it is 0, up here it is 0. Of course, at I0 is not 0 because the total energy momentum in the system is not 0. So that's not equal to 0 at I0. So this is true. And the third thing is that there exists a Bondi frame such that psi T naught is spherical symmetric at I naught as we approach from Scri plus and Scri minus. So as you approach I naught from Scri plus and Scri minus, then the statement is that this is actually spherical symmetric. Now, why is this important? This is the only last technical point, and then I'll maybe stop. Why is it important? It is important because now there is a Bondi frame like that, so I can solve my problem that you were asking me before about. Namely, I can say that, well, you just go to that Bondi frame and evaluate the super translation in that Bondi frame, evaluate the super translation in that Bondi frame, the unique Bondi frame in which it is actually that. And now I know what I mean by the same super translation here, so same super translation here, because I tied them down by what psi 2 does up here. And now I ask, is it true that the Hamiltonian across here is equal to the Hamiltonian across here? And then they say yes, the answer is yes, and that is Andy's theorem. But the reason why it is not as impressive as it sounds is because the answer is 0. Namely, all the supermomenta, I'll show you in a minute, all these supermomenta are just 0 on Scri, and they're 0 on Scri. So we happen to be in a space of solutions in which the flux of supermomentum across Scri minus is 0, and flux of supermomentum across Scri plus is 0. In fact, yeah. So therefore, we are saying 0 is equal to 0. So it's a bit like saying, I would like to show you a conservation of angular momentum. And what I'm going to do is to look at spherically symmetric systems. And then I show that the angular momentum is constant. It's not a trivial statement, right? Because maybe it is spherically, I don't know. Okay. So the statement is that if you want to show angular momentum is conserved, you should be showing it for systems which are general, not spherically symmetric.
So you're saying that generically you can't find this side to this frame with.
Yeah, I don't expect it to be because yeah.
This is perhaps an indication why the boundary conditions are or the fallout conditions are too special.
Too restrictive, right? Exactly, right. But it's a ball, but still just too restrictive.
Yeah.
So, in the other boundary conditions, or the boundary conditions used by the other people that you mentioned that are is this possible?
The thing is that these other people don't actually show you the fall off as you go here, as you go there. But I'm in the process of working it out. I think it is not true, but I'm not 100% sure. I'd like to work it out. I mean, I could also just write to them maybe. Yeah, so I don't know. So that will be good if that is the case. So now let me just say why this is the case and that why this angle is 0, and then I'll stop. All right. There's also this last part, just to solve gravitons. I'll just postpone it for some other time. I mean, if there is interest, this soft graviton also fits in very well with the proposal of Hawking, Perry, and Strominger about the black hole information. And then there also I can tell you what I believe to be true. It's all based on this. But on the other hand, I think that this is only a suggestion. Why it is only a suggestion? That it only opens a door. It doesn't even tell you what direction to go. It just opens a door so that I can do it some other time. I'm here until the middle of September, so if there is interest, I can do that. So last thing that I just want to do is to tell you this thing that I just claimed as to why this is the case. And that just follows from here, right? We just said that the difference between these two charge integrals is this Hamiltonian. So therefore, this Hamiltonian that we looked at, let's see, is just equal to limit as u goes to infinity, limit of this Hamiltonian is equal to, so this Hamiltonian is on Scri plus, that is just equal to, so this Hamiltonian on Scri plus is just equal to integral on I0 of this quantity that, let's call it charge integral, so let me just call it Q d2v minus integral at I plus of q into t. Right? Now, so that is what this quantity is, right? Because the total flux across crack of this is just equal to the difference between the charge integral when you move this cross section up and move this cross section down. So that is what this is, total. And similarly, C minus on sky minus, that is just equal to I naught of q d2v minus I minus. So for sky to calculate the total flux here is equal to the charge integral here minus the charge integral here, and the total flux here is equal to charge integral here minus the charge integral here, minus q times d2v. But NAD goes to 0 at both ends, therefore this term goes to 0 at both ends. Okay, and now psi 2 goes to 0 at I plus and I minus, therefore this term also goes to 0 at I plus I minus, therefore this term is 0, and I did say that explicitly, and this term is 0. So H plus is just given by this, the charge integral here that I wrote down, and the charge integral here that I wrote down. But since the new tensor is 0, let me write down this explicitly, the charge integral. I get alpha times psi 2 naught, alpha times psi 2 naught. But now we say psi 2 naught is actually spherically symmetric. This is spherically symmetric, and this is supermomentum. So this is YLM with L bigger than 2. Therefore, this quantity is 0. This quantity is 0. Therefore, H plus is 0 and H minus is 0. So it is true that the supermomentum here is equal to supermomentum here, but the reason is because they're both 0. And somehow this is not emphasized anywhere. And I just wanted to sort of explain to you my understanding of it. I mean, it could be that I'm wrong somewhere, and I would like to be corrected, but I think that. So I'm not saying, I think it's a very interesting suggestion, especially in light of what I did not tell you about soft gravitons. Let me just tell you about that soft graviton thing. So the idea is, one minute, I won't write anything down. So what happens with soft gravitons? The idea is that you want to get a handle on this conservation law coming in from quantum gravity, right? So the idea is to just do sketching S matrix theory. Of course, it's ultra, it's not renormalizable. So we just put ultraviolet cutoff because we're interested in infrared problems up here. And then the statement is that we're asking is that is some quantity calculated here is equal to the quantity calculated here. But the Andy says that you're going to S matrix, and he says that the S matrix must commute with the generators of supertranslation. Why? Because his reasoning is that the S matrix is exponential of the Hamiltonian. But okay, and therefore the question is, what is the Hamiltonian? So he says the Hamiltonian is the one which is obtained by putting alpha equal to 1. Because that's like the energy, right? That's like the energy up here. So just put alpha equal to 1, then you will get S matrix is exponential of that. Then he says that, but what are supermomenta? Supermomenta are these objects with non-trivial alpha. But we know that all supermomenta commute with each other. Therefore, each supermomentum commutes to the Hamiltonian. But since Hamiltonian is exponential of the Hamiltonian S matrix, therefore supermomentum charge must commute to the Hamiltonian. And because it commutes to the Hamiltonian, that means that if the S matrix commutes to the Hamiltonian, right? If the S matrix commutes to the with supermomentum charge, then the supermomentum charge is conserved. This is the argument. And to me, this has many gaps in it, right? I mean, it doesn't seem to be completely, it's not clear that the S matrix is the Hamiltonian, etc. And then he says that, well, let us go to perturbative gravity and actually do calculations. And he takes this S matrix times the supercharge, the quantum version that I was writing down up here, and he looks at the matrix elements, and then uses Weinberg's soft graviton theorems to show that the matrix elements are equal to each other. So, but of course, only to linearize order that is done. But then there are formal arguments to say that this should hold to all orders, including loop diagrams, order by order in perturbation theory. The problem is that if you look at the S matrix, it is infrared divergent. If you look at the charge, it is infrared divergent. So these are formal manipulations, and whether these formal manipulations really lead to some result is an open question. Sometimes they do, sometimes they don't. And just to point out, those of you who are interested, there are a few kind of careful discussions of this thing in the literature. There's a paper by people associated with algebraic quantum field theory, which appeared after, this year after the Hawking-Perry Strominger proposal came up. And this paper is by Jen. His preprint number is 1604. 0417. And there is another paper which appeared much more recent in July. This appeared in June, I think, or I guess April, and this appeared in July. This is Mirbabai. And this is 1607, 0312, which point out that there are problems. The first paper points out that the charge has infrared divergences, therefore the fault manipulations are formal, and the second paper points out that the S matrix has its problems, and if you correct it, then this phenomena just disappears. This phenomenon of S matrix commuted with charge integral actually just disappears. So I think that this is an interesting, technically hard problem about these infrared divergences. Maybe there is something in this suggestion, but classically, it is proved in a rather uninteresting case. Maybe one can prove it in more interesting cases. And quantum mechanically, it has this formal aspect. Okay, so I covered everything I wanted to say. Thank you. Yeah. Yeah, first.
Could you say something about superrotation?
Yeah. So the formula for superrotations has not been a satisfactory formula in the literature. First of all, there is a formula. In the paper with Schreibel, we gave the fluxes completely. The question is whether there is a charge integral from which these fluxes come. People have charge integrals written down in the literature, but they are rather messy in the sense that they use Newman-Penrose tetrads and all kinds of extra structure. One would like to have clean formulation. And this clean formulation was just done a few months ago. It is not yet written down, but we understand that. But that is not part of this thing at all. This whole thing is, so there are charge integrals, there are fluxes formula, and we have the balanced law, both cases. Of course, we don't know anything about S matrix. Yeah. Please.
Historically, the energy momentum historically is described as the came out of the Einstein equation, a considered
Energy moment. Oh, okay.
It's supposed to be equivalent of the electromagnetic energy weight. This is what Einstein originally used. And it's not conformal osmosis. It's not phase different. So how does this whole story relate to your H?
Right. So so the question is that those of you who didn't hear, the question is about the energy carried by gravitational waves. If you try to give a formula in the physical space-time, we don't have a gauge invariant formula. People use pseudo-tensors, but that depends on the choice of coordinate. That depends on all kinds of things, which is not invariant, period. And we know there is no such a invariant notion of energy, localized notion of energy. But the statement is that there's a perfectly nice notion when you go out to infinity. So if I want to write this as some integral on a space-like Cauchy surface, or on a partial Cauchy surface like that. So for example, I got this energy momentum, and if I want to write down like that, then I don't have a canonical formula here at all. Different people will write down different formula, I'll get different answer. So locally in space-time, I don't have a notion of local energy momentum or mass. But asymptotically, there is a gauge invariant quantity, because you go to infinity, then the structure simplifies. Now this is the 0th order answer. The first order answer is that mathematicians, particularly Muton 1 and Yao, they have been spending several years now, 2 or 3 years, on trying to define a quasi-local mass formula, not supermomentum or anything, but just quasi-local mass formula. They're extremely ingenious. It is very complicated mathematics. It's way beyond me because it has to do with all these theorems in geometric analysis. But basically, given any two surface, they want to embed it in a certain way in Minkowski space-time with some restrictions and do some manipulations there to come up and give you formula in the physical space-time. This formula has many nice properties. It does give you Bondi energy. It does give you the ADM energy at infinity. It has nice property in the limit. It should behave in a certain way. It does behave in the limit. But in stationary space-time, it doesn't agree with Kolmar integrals. And so I don't know. So the statement is that there's a lot of work that really high-powered mathematicians are trying to do to see if there's a quasi-local definition which is gauge invariant.
Different question.
Okay. Awesome.
Massive fields never get described.
Very good.
So I can imagine that I've got this theory where I've got just massive fields in the past. Nothing comes in over Scri minus. Some of those massive fields then decay into massless fields. Now I get all kinds of junk coming through Scri plus. And obviously the energy there isn't conserved.
Right. So what has to do, and this has not been done. Let me first say what has been done recently and then tell you more things. So but recently what people did was in electromagnetism. Because same thing, right? I mean, if I charges, and the charges, I mean, so there we're talking about the total charge in some ways. So what happened? So what they have done is they looked at the Maxwell fields going out to infinity, and then they have blown up this I0. So what they do is, this is to me counterintuitive way of doing it, but that's what they did. Sorry? I plus. I said I0, I plus, I meant I plus, sorry, thank you. There is a construction due to Kurt-Cutler which actually blows up I plus, very similar to the way that he followed what we did at I0. It blows up at I plus, and then you have to take into account what happens at I plus together with what happens up here. But again, there are open questions about how do you match the two ends of I plus, so to say, with it, because there's a hyperboloid up here, and how do you match it? So to avoid these questions, what these people did was to take a cross-section up here and consider a family of hyperboloids. And such data do exist, and that's perfectly fine. They consider a family of hyperboloid like that. So if you like, the Cauchy surface for these people is really, so these people are Campiglia, and Nanta. And what they do is they consider such surface up here. And then their Cauchy surface is going to be part of Scri up to this cross section, and then this space-like surface up here, coming down. And then they are doing these calculations in this part of Scri space-like surface up here. I understood the first order. I don't understand in great detail, but they are competent. He's my student, he is my postdoc, they're careful people. I mean, I know them, that's what I mean. So they're careful people, and so they are actually doing, so I like to understand that paper better. But and so similarly, you're completely right. At full gravity, one would actually have to take into account what happens here. I mean, otherwise, I mean, if you just do vacuum case, right? I mean, the gravitational waves come in, going out, and you get some insight. Of course, that's not very valuable, but we need to do that. Sorry, you had a question.
Yeah. Is there a Newman and Penrose identified 10 conserved quantities, and they had L equals 2, and I don't think psi 2, 0 also appeared. Are those related to?
No. Those conserved quantities are absolutely conserved. So that is to say, they are not changing at all. There's no flux of those conserved quantities. They have been a little bit of a mystery as to what they are, and they continue to be mystery. I don't think anybody completely understands those quantities or their physical meaning and so on. I don't mean that we don't know anything at all, but we know very little. Okay, so I guess no other questions, so good. Thank you.